Welcome back. Okay, so let's go through that formalism that we just created, and now resolve it to specific terms that apply to to continuous space systems and to discrete space systems. Now, in theory, we could generally apply the same framing and the same mathematics to both systems, but in practice, the tools and techniques that have been applied, or that will be applied to the various kinds of systems, have stemmed from different sources. And so the language that's used to describe them, and in fact the language that's most convenient to describe them, are going to be different. And so we'll go ahead and distinguish the two of them when we're talking about continuous or discrete space systems in particular. If we're talking about systems in the abstract, we'll generally use the same letters and the same numbering, the same mathematical language. And it turns out those in practice work very well for the continuous space systems. So we can start with our state. In our continuous space systems, we said our state was a quantity x of t. And because it's a continuous space, because the signal x is a continuous variable, we're going to say that x of t is some vector value of dimensionality n. That is, x of t is drawn from Rn for all t. And of course, I'm not here distinguishing between continuous time versus discrete time. T could be a real value, or t could be an integer value. Nonetheless, x is drawn from this. And this right here is known as the state space. So we have our state. The set of all states is the state space. Now the state, it turns out, is is going to be the quantity that very strongly determines the nature of the system. And so we may use the term continuous state system instead of continuous space system. Now, once again, it's important to note that when we talk in this class, we're going to distinguish between continuous space and discrete space, applying to all of the quantities within the system. However, we may have systems where perhaps some of these quantities will be continuous and some of them will be discrete. We're not going to discuss them in this class. So when we talk about continuous space systems, we can replace it with continuous state systems, and everything is going to apply equivalently. And so another notation that we will apply here, if we talk about our state being the lowercase value x, the set of all states that could be the set of all values that could be a state will be the capital value x. Actually, let me write this a little bit more precisely. That's this. So we may have a subset, a subspace of all of Rn that where our states are only allowed to be in. And we're going to use that, we're going to call that as capital X. So our lowercase state x, our lowercase x is the state, the capital X is the state space, and that lives within some n-dimensional space from R to the n. And for that, we will then say that the size of this state space, and because the state is oftentimes the most distinguishing characteristic of a system, the size of a system, we'll use double bars to represent that, is the dimensionality of our space. So if x is an n-valued vector, then the size of the state space x and the dimensionality of the state space x and the size of the problem is going to be n. This is what we're going to use, that we use the x for the generic system. We're going to use that for continuous space systems. For discrete space systems, we're going to use a different notation. We're going to call our state S. And just to make notation a little bit simpler, since we know that in a discrete space system, we're also talking about discrete time, we'll just give the time index as a subscript. Similar to the continuous space, if we talk about the space that the state lives within, the set of all st is the capital letter S, and that's our state space. Now, because it's a discrete space system, because S is a collection of discrete values, we can't say anything further about the state space. The state space itself can be anything. If we're talking perhaps about a system that involves a flip of a coin, in that case, the only thing that matters, the only outcome, the only output of the system that matters, is whether the coin flip was a heads or a tails. And so our state space may be the set heads or tails. It is a set, which is a mathematically sound quantity, but it's not the subset of any, necessarily the subset of any real space. And so in this case, we're going to define the size of the problem, define the size of the state space, as simply the number of states in our state space. The number of different values our lowercase s contain. And we're going to call that n. And in particular, we're going to call it n of the states. Great. So that's our state. How about our input? We have our input to our system. In our continuous space, we define that as u of t. U of t, we can call it an element of some input space, u, which is going to be a subspace of the reals again. This time, it can be a different vector value. We're going to give it some size r. Okay? And so again, we're going to have some vector value input coming from an r-dimensional vector space, and that'll be our continuous space input. In our discrete space, we're similarly going to have an input to the system, but rather than call it u, we're going to call it a. Again, indexed by t. And this is because it's going to be known as an action. The state is still a state, but now we have our actions. Our actions similarly come from, sorry, it should not be an equal sign, this is an element of. Our actions similarly come from some action space. And of course, the size of the action space is just an n. And now we'll have our outputs. In our continuous space, we have our function z of t. Suppose we can give our z of t some output space, which is a subset of some other dimensionality of real values. We're going to give this a size n. Well, in our discrete space, we'll have outputs, but instead we're going to call them observations. We're going to call them O, lowercase o of t. And you might be getting a hang of the pattern now. Our O of t is going to be within some output or some observation space, capital O. Just a note on my handwriting. If it's a capital letter, I'll try to include serifs. There's no real good corner to put a serif on the O, so I'll give a little twiddle. But it's just lowercase values are individual quantities. Capital values are spaces. And of course, the size of our output space is, again, some both sides there. And those are our observations. You may see some slightly different notation. Instead of an O, you may see an omega, or a different style of capital O. In general, these notations will be obvious when you get started. Things will get a lot more confusing as we go, and as we'll see that in the next steps. Once we have our input, our output, and our state defined, we can go ahead and start defining our equations. So remember, we had two equations that defined our system. You should be able to write these down by memory. We have our first equation, which says what happens to x. Let's go ahead and write these down and say, in continuous space, we'll allow either continuous or discrete time. So either in discrete time, we'll have x of t plus 1, or in continuous time, we'll have x dot of t. We'll generically call that x prime of t. And we'll say this was our function f. And f takes as input x of t, u of t, w of t, and t. This equation, we can either call it our state equation. This is also known as our system dynamics. Okay, so we have this functional relationship, which takes in some real valued inputs, produces some real valued output. We can throw in a bunch of mathematical operations, whatever we need, to describe this relationship. And that'll describe how the state evolves over time in a continuous space. How about in a discrete space? This is going to be challenging. It'll be difficult to write out a system like this because this functional form, we know how to write functions that apply to real valued numbers or vectors. What if our discrete state space was something like heads or tails? We don't really have a mathematical function that operates on the quantity heads. So we're going to need to come up with a different way of writing out our state dynamics. Why don't you take a moment right now to try to come up with some ways that you can describe a relationship similar to what we've described over here, but using mathematical set quantities and elements of sets rather than real values. So pause this video and see if you can brainstorm some ideas, and then come back and join us. Okay, so hopefully you've come up with some ideas. What we have is a relationship between the state at a current time, the input or the action at a current time, the state at the next time instance, since we are in discrete time, and some amount of uncertainty. Well, if each one of these quantities, the state, the action, the next state, is drawn from a set, we can just rearrange this statement to pull out this uncertainty on one side and all of the other quantities on the other. That is, the way we'll define a state update is by capturing a complete description of all probabilities, the probability of having a state, taking an action, and ending up in the next state. And so, given the state which you started in, and the action that you took from that, and ending up in a particular state, we can comprehensively compute over every triple of state, action, next state, the probability that that is a thing that happens. That captures this uncertainty, W. If we wanted to explicitly include this time dependence, we could go ahead and say that these probabilities vary over time, and each probability is a function of time as well. So we can go ahead and include that there. And we have to do this for every single possibility. We'll enumerate every single probability here. We can write this, this set, we'll give it a set value capital P. And these are going to be known as our transition probabilities. We're going to use the letter P. You may see sometimes it's called the letter capital T. We'll use this probability and we'll give it some other aliases just to help us simplify notation a little bit. So we may call this the function P of S, A, S prime. So again, S is the current state, A is the current action, S prime is the next state. And of course, this could be indexed by T. Sometimes this is written out as P of S prime given A. And let me write this over here to save some space. So we could have P of S, A, S prime. We could have the set of P of S prime given S, A. That is the probability of ending up in a particular state, given that you started in a state and took an action from that state. Sometimes we may see it written as P with a subscript SA. So the probability where you start in state S and take action A of ending up in state S prime. So we'll see all these notations. Fundamentally, what this is referring to is the probability of a particular state action next state triple. These transition probabilities serve the same functionality as our state equation or our system dynamics. And in a very similar way, we can talk about our output equation. And again, you should be able to write this down from memory. Our output equation says that Z of t is some function h of our state, input, noise, and possibly time index. Depending on how we defined our state, we may not have this explicit U dependence in this equation. We can go ahead and leave it just for notational completeness. You should be able to see some parallels between these two equations. And in doing so, come up with the corresponding system out here for our observations. Take a moment and try to do that yourself, and then come back and join us. Okay. Hopefully, you were able to directly see the parallels, just pattern match between X, U, some noises, which will then translate into some probabilities, and outputs. And therefore, we can say that what we're trying to come up with is a set of probabilities of being in some state, taking some action, and generating some observation, perhaps at time t. And again, similarly to above, we can write these as in various forms. Now, the letter P has been taken by the transition probabilities, so instead we'll give it a new letter, and this is where notation starts to get confusing. We'll just go ahead and call it O again. So we can either say that rather than it's, has some state action next state, we can just call this the probability of, let's do this. So we could write this as the probability of O given S and A, similar to this one. Or we could just identify this particular probability with the observation itself. That is, an observation, it may have a label that says this is what we saw, but mathematically speaking, an observation is a function that relates a current state and a current action to a probability. So again, this is just some mathematical conveniences. We'll go ahead and use whichever one is most appropriate in our mathematical statement at any given time. But what this is philosophically saying is an observation is no more than the likelihood of that observation happening. No more, no less. Okay, so one thing we can figure out now, at least in this discrete space, we talked about the size of this problem as being the dimensionality, the number of elements within our state space. That's why it deserves its own line. This is something that indicates, in general, the complexity of a problem. But within this framework, we can see that the transition probabilities, that is the corresponds to the state dynamics, is just another set. What is the size of this set? Let's go ahead and assume for convenience sake that we're talking about time invariant systems. So there's no explicit dependent on time. If there were, we could index our time over here to say that at any given time we'll have a set of probabilities. But if we were talking about a time independent or a time dependent, time variant where we just look at one time, how big is the set P? Or how big is the set P sub T? You should be able to compute that. Knowing the size of all of our other sets, we have a probability associated with every state, every action, every next state. So for every one of ns, there'll be one of na. And so for every one of the pair ns of ns and na, there's another ns number of future states. That is the size of the transition probabilities. Go ahead and write that down here. It's squared in the number of states times the number of actions. Similarly, we can describe this. I guess I didn't write that down. Again, just by identifying each observation with the function, either we could say that this, if we do that, then we can say that there are n capital O, that's an O, just to be clear. N capital O elements in this set, but each element is this function. And a function in a discrete world is no more than just another set. So go ahead and write this down. So the size of each function, the size of each set that describes an observation, is just the number of states times the number of actions. The number of state-action pairs. Which means if you wanted to write out the collection of probabilities like this, then this wouldn't be the observation space, but this would be the set of observation probabilities. That would be the number of states times the number of actions times the number of observations. Okay, so this gives us the mathematical statements that we're going to be using in our systems. This right here has a term. We're getting this set up to be a Markov decision process, or an MDP. A discrete space system, or a discrete state system, is going to be, we're going to be considering the Markov decision process formulation to build on that. once again, we see this word markup. Right? This formulation and the math that we derive from it is only relevant for systems where the state is Markovian. And since we're going to ensure we're going to define our state to be markup, then we will be able to use this framework to talk about discrete space problems. When we talk about continuous space problems, we're going to use this. And we'll use the letters X, U, Z, F, and H in general to refer to states, inputs, outputs, system dynamics, and output equations. And so now that we have this framework, let's take a step back and figure out how to apply this general topic of systems to the specific material of robotics. But before we do that, this may be a good time to take a break. Get up, stretch around, get some blood flowing, and then come back and join us to talk about robotics problems.